Hello everyone and welcome to another video. So today I'd like to continue our discussion on time domain analysis for dynamic systems by looking at a different type of metric. This is what's known as the time to double, and we're going to look at this for both a first and a second order system. So this is going to be an extension and a continuation of our discussion. Remember, in our last video we actually looked at deriving what we called performance metrics, right? Things like percent overshoot, settling time, things like that. And we looked at how does a dynamic system respond to a step input, and we characterized it using these performance metrics. So what we're going to do is let's extend that idea now to this idea of another type of, quote unquote performance metric, and that is the time to double. Except in this case, we're not going to look at stable systems like we did in the previous situation. In this case, what we want to look at is actually unstable systems. And instead of looking at how does an unstable system respond to things like step inputs, instead now what we want to ask is how does this unstable system respond to changes or non-zero initial conditions? So I know that might sound a little bit esoteric, but surprisingly, it shows up quite a bit. And I know you're probably asking yourself, who could possibly care about, performance of unstable systems or characterizing unstable systems? Well, here, this guy right over here, he probably cares about how an unstable system is going to evolve over time. So you can see right here, this is effectively a giant inverted pendulum, right? He's trying to knock down this giant silo, which, yeah, think about it like an unstable pendulum. And as soon as he gives it enough of an initial condition perturbation, this thing is just going to start falling over. Well, he probably cares a whole lot about how long does it take to go from 1 degree of deflection to 2 degrees of deflection, or to double that. How about how long does it take to go from 2 degrees to 4 degrees, or from 4 to 8, or to 8 to 16 degrees, right? He's going to want to know how fast is this tower going to come down so he can get out of the way. So this is a case we're going to see which falls under the category of time to double for a first order system, because the system just, once you start perturbing it, it's just on its way to instability and off to infinity quite quickly, all right? Another case where you might see this is, what about with the second order system, right? We've got enough of an intuitive feel now of these dynamic systems that we now understand that in certain situations, second order system can behave in oscillatory fashion. So again, here's a situation showing a real life example of an unstable oscillatory second order system. And as you can see, now what we get is we get these oscillations that increase and increase in magnitude until your system goes to infinity or blows up or breaks itself, right? So again, in this kind of situation, we want to understand how much time does it take for that small little oscillation to amplify to double the magnitude, to quadruple, to 8 times the magnitude, right? We want to understand how fast does the instability work its way towards infinity, okay? So that's the physical intuitive sense of what we're trying to look at. Let's see if we can formalize this and derive equations to exactly understand from first principles how to compute the time it takes for the signal or the system to double in magnitude, okay? So the easiest thing to start off with is, let's start with a first order system, okay? So first order system, it's pretty standard. Let's just use our standard first order differential equation, right? It's some x dot plus px is equal to 0. So again, you can see here, there are no external inputs here, right? This is a homogeneous first order differential equation. But let's consider having non-zero initial conditions. So we want to understand if there's a non-zero initial condition, and if this system is unstable, we know that this signal x should go to infinity, correct? Okay, so just to verify that, let's do this again, like I said, from first principles. Let's go ahead, solve this first order differential equation. I'm going to use the Laplace technique to do this, right? Again, we had a dedicated series of videos talking about how to solve linear ordinary differential equations of an arbitrary order using the Laplace technique. So feel free to check those out if you're not familiar. But again, all we're going to do is take the Laplace transform of both sides. The only term that's interesting really is this x dot, right? So we end up with an s x of s minus the initial condition. Okay, so again, solving this now for x of s, we can get the response of the system in the Laplace domain to this non-zero initial condition, right? So now all we have to do is we have to take an inverse Laplace transform of this. So again, you do this in Mathematica, you compute the inverse Laplace transform by hand, you look it up in a table, whatever you'd like. you end up with this, right? So we end up with x of t, it's just this exponential signal, right? It's the initial condition times e to the negative pt, right? And you can go ahead and plug that into your original differential equation and show that it does satisfy the initial condition, or the differential equation, and you can show that this satisfies the initial condition. I mean, you can see it right now, right? If t is 0, this whole term goes to 1, and you're just left with the initial condition. So this is the solution to this first order differential equation for any p-value, okay? So now what I'd like to consider, since we're talking about unstable systems, we want this p to actually be less than 0, right? Because if p is less than 0, the roots of this, I mean, I guess you can even see this probably, right? We do a rough calculation, right? It's something like s plus p equals to 0, right? That's a characteristic equation. So if p is negative, if you had something like s minus 3 is equal to 0, right? The root, or the value of s, we would have is, the root is what? It's positive 3, okay? So you have a positive 3 as the root, and this is the case when p is equal to negative 3. And you can even see it in the response now, right? What happens is if p is negative 3, this becomes e to the positive 3t, which is a signal which kind of looks like this. In fact, I think what I drew here, sorry, I probably should have used the same number. I think I used 2, p of negative 2. So you have all these should be 2's. The root is at positive 2, and you get this thing, which this looks like e to the, some initial condition x naught, e to the positive 2t. Right? Again, this is with p equals to negative 2. Okay? So you get a signal like this. And you can even see in this example that I've drawn, I guess I used an initial condition of x0 is equal to positive 1, right? So the signal starts at 1, but if you have this p-value, you get this exponentially increasing curve. Okay? So now, the idea with time to double, right, is we want to ask ourselves, okay, how long does the signal take to double? So let's pick some value like, I don't know, 10. Okay, let's go ahead and look at, here's the time when the signal is 10. Okay, and now I want to understand how long does it take for that signal to double. So now what I need to do is I need to look at, okay, up here at 20. How long does this take? So this right here is the time to double that we're talking about. So this time is, let's call this t double. Okay, and now you might ask yourself, okay, well, is that the same thing? Like, what if I picked another value and tried to look at the doubling? Let's use another color. How about green? How about 25? Let's start here at 25. Okay, so here's the time when the signal hits 25. Now again, I want to look at when does the signal double, so I need to now look at 50, right? That's 25 times 2 gets us up to 50. So that's here. So again, in this case, this now is t double. So I want to understand how can I calculate this, okay? This time. Okay, so I think everyone will agree that the relationship for the time to double is I'm looking at the signal at time t plus t double. If I divide that by the signal value at time x of t, that should equal 2, right? I'm looking for a time to double. That goes along with this picture right here. Okay, so that's pretty easy. All we need to now do is plug in our expression for x of t, right? Plug this in to this relationship. So the numerator becomes this. The denominator is literally this term, right? Because it's just x at time t. And you can see a bunch of stuff cancels out, right? This initial condition cancels out. This e to the minus pt and e to the minus pt cancels out. So we're just left with e to the minus pt double, right? You just end up with this. So this is beautiful. Look at this. This is actually quite elegant. So I'm trying to solve for t double. So just take the natural log of both sides, right? You take the natural log of both sides, you get this, and then the stuff in the exponent just comes down. Now I go ahead and solve for t double, and you end up with this expression, right? So here we go. This apparently is the time it takes to double, okay? And again, maybe what we should make a quick note of is really we are interested in the case where p is less than 0, right? So maybe we should have put that in here, right? This is the idea. The time to double is this equation with the understanding that p is less than 0. P is negative, okay? So the denominator is always going to be some positive number. Now, let's examine this and ask ourselves, there's some interesting behavior with this equation. Notice, first of all, the initial condition doesn't show up anywhere in this expression. So no matter what initial condition you start your system with, the time to double doesn't change. And furthermore, notice here that time t also does not show up. So this doubling time is the same everywhere. So this is a really fascinating part of this framework, is that it doesn't matter where you are trying to look at doubling, it's always going to take the same amount of time. So you give it this t double and the signal will always double in size in that delta t. So again, pretty darn interesting, right? Okay, so again, let's take a step back and think about what is this p-value and what does this actually mean? So coming back to our discussion over here, right? We said that this p-value is effectively telling you where the location of the root, right, or the pole of this system is. So in this case, when p was -2, you had a root at +2, which is what I've drawn right here, okay? So in this case, this red X is the pole of the system. And we see that if we plot the pole location in the real imaginary plane, we see that it's in the right half plane, which again, for those of you who have been following along with our discussion on controls and ordinary differential equations, you know that if you have a pole of a system in the right half plane, it's unstable. That's exactly what we've just shown here, right? This pole in at s equals +2 leads to exponential increase. And again, this pole at s equals +2 corresponds to a p-value of -2, okay? So this is what we end up with. This leads to instability. And in fact, what we can now do is we can calculate for this particular case, what's the time to double if your system has a pole at +2? We'll just use this equation, right? So let's use our example of literally this blue line that I showed with an x0 of 1. And again, we just saw nobody cares about the initial condition. I don't need this information to calculate our doubling time. All I need to know is where is that pole located. So the pole is located at s equals +2, which corresponds to a p-value of -2. So just plug that into this equation, right? It's natural log of 2 over -2 or +2 if you want to call it that way. You calculate this and you end up with about 0.34. So what it's saying is this time to double is about 0.34 seconds. So you've got about 1/3 of a second before the signal doubles, and then you got another 1/3 of a second before it doubles again, and then another 1/3 before it doubles again, right? So again, in this case of that, that falling silo, maybe that's okay. Maybe this gives you a couple of seconds to get clear, but you can see that as this pole moves in this direction, right? As you get more and more unstable, what that does is it changes its denominator, and this relationship you're actually going to see. In fact, we'll do a formal plot of this later, but what you've got is you've got a situation where the time to double, as you start looking at the positiveness of the pole, right? As this increases, as your pole gets more positive, the doubling time decreases quite sharply. So this is an interesting behavior. And again, this passes the duh check, right? If your pole is further in the right half plane, it responds more quickly, right? Instead of a, instead of an e to the +2t, if this was e to the +20t, this would be way steeper, right? And your doubling time would go down, okay? So again, this all checks out. This is pretty easy. This is pretty reasonable. Now, what if we want to talk about a second order system? So give me a second to erase the board, and let's just replace a lot of this analysis with a different quote unquote plant model. All right, so now let's turn our attention to a second order system. So this is our standard second order homogeneous differential equation. And again, to plug our other video, remember we had a completely dedicated video talking about what these standard second order differential equations were, what this damping ratio zeta and this natural frequency omega n kind of physically corresponded to. So if you want, feel free to check out that video first to get a little bit of an intuitive feel. But we can also approach this from a sterile mathematical perspective and just say, let's do the exact same thing we did with the first order system over here. So all we want to do is just understand what's the solution to this second order system, right? So now we've got two initial conditions because this is a second order system. So we have an initial x and an initial x dot. But otherwise, we're going to do the exact same thing. You're going to take the Laplace transform. Now, I'm going to skip a few steps because, in fact, you're going to see I'm going to be skipping a lot of steps here on the board. Maybe this is a great time to mention, right? Remember all of the lecture notes, code, anything like that that you need for any of these lectures that I'm giving. Feel free to check out the description of the video. There should be a link to where you can obtain lecture notes. So I'll talk about them at a high level here up on the board, but if you want to look into the nitty-gritty and look at all of the calculations and verify mine and see how I got here, please check out those typed up PDFs. That's going to be a lot easier way to follow along with it, but I'll give you the high level roadmap. Like we said, just go ahead, take the Laplace transform on both sides, solve for x of s. So we solved this in the Laplace domain. As you can see, both initial conditions show up here, but you can basically massage it to look like this. Okay, then you're going to go ahead and take the inverse Laplace transform. Again, I do that in Mathematica. You can do this any way you'd like, and you get this ugly thing, right? At the end of the day, and you know, if we take a step back and ask ourselves, does this seem reasonable? It should, right? It's the solution is basically it's some constant e to the root 1t plus some constant e to the root 2t. That's basically what you're getting out of this thing, right? It's just that these constants a and b, they're kind of ugly, right? And again, I'll write them up here on the board. It's probably impossible to read on the screen, but that's what the lecture notes are for. That's what this looks like. It's just some c1 e to the r1t plus c2 e to the r2t, okay? Now, what we can do is let's massage this to get this into a little bit better form that we might be able to understand. So let's go ahead and make a couple of substitutions. Notice that this term zeta omega n shows up a lot. Let's call that thing sigma. And then there's this thing here that shows up a lot, right? This square root of -1 plus zeta squared omega n squared, okay? Let's call that just plain old omega for now. And again, if you do these substitutions, you make a little bit of algebraic manipulation, you can get it to look like this, right? Where now we can basically pull out this e to the minus sigma t on the outside. Then we have, again, it kind of looks like a, you know, constant e to the root 1t plus constant e to the root 2t. Okay, great. Let's now make another substitution. Let's go ahead and you can kind of see here if you sort of flip the sign of this, you'll get a -1 root -1 that turns into an I. So I can rewrite this, and let's now make another substitution of omega d. Sometimes this is referred to as the damped natural frequency. Obviously, if you saw our previous videos, you know why. This will also come into play in a second, but it's just some other algebraic substitution. I'm going to go ... and I can basically get this to look like this, where it looks very similar, right? But now I've popped that I out, okay? So now you look at this and you say, okay, hey, you know what we can do? Let's apply Euler's formula, right? Because this sure looks like it's just e to the something I, e to the something I, right? Remember Euler's formula said that I can write e to the something I as basically a cosine plus I sine of that thing, okay? So I can basically rewrite this as a cosine and sine term. And again, I'm going to skip a bunch of steps. That's what all these ... dots mean. And again, check out the notes if you want to see exactly what I'm doing. But what's fascinating about this process is you do this, and you know what? These imaginary terms go away, and you're left with this term. It's just same thing on the outside. It's e to the something t, right? This is some exponential term. But then the thing inside the parentheses, it's just cosine plus sine, right? Because if you look at this, it's just some coefficient of cosine plus some other amplitude of sine. So these two sine and cosine waves are not the same amplitude, but they're the same angular frequency, right? Omega d shows up here. So you say, aha, well now I can use my trig identity for combining linear combinations of sine and cosines at the same frequency, right? And again, just to refresh your memory, this is what it looks like, right? If you have some alpha cosine x plus beta sine x, it's just, I can combine that as a single cosine wave with a modified amplitude and a phase shift. And again, the modified amplitude is you just take the amplitude of both of those sine waves, square them, add them together, take the square root. And then the phase shift is just this 4-quadrant inverse tangent of alpha and beta. And again, we had a completely dedicated video on 4-quadrant inverse tangent, or this atan2 function. Again, you got to be a little bit careful how you are implementing this in your analysis package, right? Some packages, like MATLAB, want the first argument to be the y component and the second argument to be the x component. So that's the convention I'm going to follow here. Mathematica actually wants it in the exactly opposite order. So again, this is one of these moments where you want to just make sure you understand what you're doing mathematically on the board versus how you're going to implement that in code if you're going to write this up. Okay, but long story short, again, take a step back. It's just taking this thing inside the parentheses, this thing, right? And all we're going to do is just combine those two cosines and that cosine and sine wave into a single cosine wave. And we basically end up with, this is what gets awesome, is this is what we end up with a whole bunch of, well, not a whole bunch, but with a little bit more algebraic manipulation, dot, dot, dots, you end up with this. So here is our response of the system. So x of t is just this. And if you look at this, let's take a look at all these expressions, right? So we know what this sigma is. It's just zeta omega n. So this is just a number, right? Same thing with this omega d, right? This is the angular frequency of the cosine wave. This is just another number, right? Because you know you're going to know zeta, you're going to know omega n. This amplitude, A, the big A here, again, it's this ugly thing, but look at it. It's just nothing more than initial conditions in zeta and omega n. So, and again, another constant. And finally, this phase shift here, this is just another constant. Sure, initial conditions, zeta and omega n, but you can calculate this. This is like a number like 38.4 degrees of phase shift or something like this, right? So what's fascinating, right, is the end of the day, the solution to this differential equation can be written as as basically a single cosine wave that has an interesting amplitude, right? If you look at this, the amplitude, it's actually time varying, right? This AE to the minus sigma t is basically the amplitude of this cosine wave, and it changes with time. And that's what we're going to maybe look at next is how does that change? But otherwise, it's nothing more than a cosine wave, right? And you can actually take this, and in fact, we'll go over to Mathematica in a bit, and I'll make sure, I'll show you that I'm not lying and waving my hands with all this by plugging this in and showing, but we can take this, plug it into your original differential equation. You will see that it's going to be ugly, but it does equal 0. By the time you do x double dot plus 2 zeta omega n x dot plus omega n squared x, you do all that stuff with this particular x, and it will satisfy this. It will turn out to be a big fat 0, and the initial conditions will also be met. So we can't argue this is the solution to the second order differential equation. So that's the aha moment. This is what we need to want to start analyzing. So what we're going to analyze in this case is now let's go ahead and get specific, meaning I want to look at an underdamped scenario. Okay, so again, this should be valid for any case. If it's underdamped, overdamped, what have you, right? It should work. But now let's ask ourselves, the most interesting part of these second order systems is these sort of oscillatory behavior, right? We saw that with the video of the car going unstable in an oscillatory fashion. We want to look at oscillations, and we know we get oscillations when the damping ratio is less than 1, okay? So if the damping ratio is less than 1, we now have a kind of a bifurcation. There's two paths we can now look at. One of them is what happens if the system is stable. So meaning stable means that the natural frequency omega n is greater than 0. Okay, so in this case, we have a situation where natural frequency is positive and the damping ratio is between 0 and 1, right? We want it to be less than 1, okay? So what happens is, the reason this is called stable is if you look at this expression here, right? We know this is just a cosine. This is just going to oscillate forever. The question now is, does that cosine wave decay and get smaller, or does it blow up and get bigger as time increases? Okay, so we're really asking, what does the amplitude of this cosine wave look like? And we see right off the bat in our expression, the reason we like this so much is this term right here is basically telling us what the amplitude is. In fact, let's call this thing something like h of t. It's like an amplitude function, right? It's an envelope, effectively, we're going to see. This tells us how the amplitude changes. So now, in this case, let's look at this term e to the negative sigma t, okay? E to the negative sigma t is just e to the negative zeta omega nt, right? Because sigma is just zeta times omega n, right? So in this regime, if omega n is positive and zeta is between 0 and 1, this thing of negative zeta omega nt, it's a negative number, right? All this turns into, this is effectively going to be something like, you know, e to the minus 2.5t, right? Because this zeta is between 0 and 1, and this omega n is positive. So this whole thing looks like e to the negative 2.5t, which we know is basically a decay, right? So e to the negative 2.5t decays, right? The converse situation is, well, how do we get the system, or how do we model an unstable system? Well, that's the case when the natural frequency is negative, right? And we have a zeta in the range of 0 and 1. Because in that case, this h of t, or the amplitude function, right? It looks like this, right? Which again, now, this looks like an e to the positive 2.5t, which does the exact opposite thing, right? So e to the positive 2.5 grows, okay? So let's formalize that. So what I'd like to look at now is, now we're in the regime of down here, okay? So really, maybe what we should have said is, for this title, it's time to double for a, in this case, we looked at an unstable first order system and a unstable underdamped second order system, right? That's maybe a little bit more specific title of what we're actually talking about, okay? All right, so let's do that. Let's erase some of the board and let's look at what does this function do when we are in the unstable situation. All right, so let's go ahead and plot what this x of t looks like for some constants. So I picked some initial conditions, a damping ratio, a natural frequency. Again, make sure, note here that the natural frequency is negative, right? Because that's what we're looking for in this case, is we want an unstable situation. So this is what it looks like. We'll go to the computer and look at a better plot of this in a second, but I just want to talk about the general idea right now. So this is where it gets a little bit interesting. If we start talking about time to double, okay? Now, what does that actually mean? It's a little bit ambiguous in this particular case, because if we're being strict about this, the time to double, for example, if we're right here, like we're on the upswing of this, and let's say we're here at about, I don't know, 1 unit, right? This pen's kind of dying. Let me see if I got a better pen. Okay, you're here at 1 unit. The time to double, pursuant to the strict definition, is how long does it take for the signal to go from 1 to go to 2? And that's just right up here. So you can see there's almost no time at all because the system is on its way swinging up. So the time to double in this case would be really, really small. But it almost doesn't even make sense, right? Because in some other situations, like out here, you could be looking at, okay, now the time, here's 1, right? You're at 1 unit. When does it take to get to 2 units? Well, it's actually on the downswing, so you got to wait all this time until it comes all the way back up here to hit. So again, this doesn't make a whole ton of sense if you're talking about the specific definition of watching when the signal actually reaches double its magnitude. So instead, really what we're talking about in this case is we really want to characterize the overall behavior of how these sinusoids grow. How are the overall peaks, or the max and the mins, how are those changing? So really what we're talking about is we instead should probably be looking at this envelope here, this function h of t, right? Because this is the amplitude of the cosine wave. This is how the cosine wave is growing. So we really should be plotting that. So if I plot this h of t for these particular cases, actually what's really fascinating is you get a slope that looks, it does something like this, right? And in fact, this here is h of t, right? What we might want to also plot is, let's plot negative h of t. Let me see if I have another color, maybe like a green. Okay, so negative h of t is going to get you something that looks like this. So here is negative h of t. Okay, so these are nice monotonically increasing or decreasing functions. And really what we're talking about is, what is the time to double for h of t? Okay, because that is telling you the overall sort of envelope of how this sine wave grows, right? How's it exploding, right? How bad are these oscillations becoming over time, right? So that's what we really want. So we're really asking, what's time to double of h of t, not of x of t, okay? So again, if we're talking about that, I think we'll all agree that the time to double of h of t, right? It's the same thing we solved with the first order system. We're really looking for the relationship of h of t plus t double, right, divided by h of t. This has to equal 2. So again, going back to the picture, what this means is let's pick a location. Like we're talking about, let me pick another color actually first. Let's pick 5, right? So at a magnitude of 5, where is the h of t envelope? So that is, let's trace this over to right here. Okay, so this comes down. And this is where it starts. Now I want to see, when does this envelope go from 5 to double of 5 or 10? So what I need to do is trace this over until we hit the envelope and then follow this down, right? And this is what we're talking about in terms of doubling time, correct? So the distance here is your t double. Okay? That's how long it takes the envelope to double in magnitude, and therefore being kind of a conservative estimate of how long it takes for these sine waves to get there. So again, this is the relationship. So all we got to do is let's plug this in. So and we know what h of t is. It's just a e to the minus sigma t, right? So this here becomes, let's look at this first one, right? The numerator, this is just a e to the minus sigma t plus t double. Right? The denominator is just a e to the minus sigma t, right? And that has to equal 2. And again, we get a whole bunch of stuff canceling out. So this sigma t, this sigma t, this sigma t. In fact, we end up with almost the identical expression we had earlier, correct? This is basically becomes e to the minus sigma t double, right, has got to equal 2. So again, do the same thing we did last time, solve this, and substitute in sigma is just zeta omega n, okay? And you're going to basically get the exact same thing, or really close to what we had last time, right, where t double is going to be natural log of 2 all over negative zeta omega n, right? And again, we're going to make the note that this is for the case for zeta in 0 to 1, and omega n is negative. Okay, so here we go. This is our doubling time expression. Oh, my red pen's really on the way out. Okay, that's perfect. And in fact, it looks a heck of a lot similar to what we had last time, right? So using our numerical examples over there, let's just calculate it for this particular system, right? This is natural log of 2 all over negative, what was zeta? Zeta is 1/10, or 0.1, times natural frequency of negative 10, right? So again, you see that this becomes natural log of 2, well, let's just write it out so we're not skipping any steps. Natural log of 2 all over 1, and you write this thing out and you get a numerical value. I think this is about 0.69. So in this case, it's about 0.69. And again, the same observations come into play here, right? Notice that the doubling time in this case, it's not a function of initial conditions and it's not a function of t. So again, this is a nice, elegant behavior that it pretty much behaves this way regardless of where you start in the signal and regardless of what initial conditions were used to kick off this oscillatory exponentially increasing response, right? Okay, the last thing that maybe we should do is I do want to tell you what, give me a second, let me erase some of this and let's talk about the pole locations. Okay, so the last discussion to have is let's look at the poles of that standard second order system, right? We know that the characteristic equation of that standard second order system is just going to be s squared plus 2 zeta omega n s plus omega n squared, right? And we're going to set that equal to 0. So if you do that, you can solve for s to get the roots or the poles of the system, right? So you get this expression in our underdamped case. So there's a real part and an imaginary part to these poles. Now, what's fascinating about this, again, is notice, right, the real part of these poles is negative zeta omega n, right? Which is exactly the term that shows up in our doubling, time to double expression. In other words, the way to think about this is that if you have a pair of complex conjugate poles for your system like this, right? If they're in the right half plane, we've got a problem. We're in this regime. Things are exploding. Now the question is, how fast are they exploding? So we see that as this real part, as it becomes more positive, okay? So that means that this negative zeta omega n, right, it starts getting, this denominator starts getting bigger and bigger and bigger, right? As omega n gets more negative, this term gets more positive, right? So these poles start moving to the right, okay? So the more unstable your system becomes, you can see that this t double, it starts going down. In fact, we'll go plot this in Mathematica, get a real plot, but this is the rough shape of it, right? So as you become more unstable, aka the system responds or explodes quicker, it makes sense that your doubling time decreases, right? So another fascinating connection, and again, if you connect this with what we talked about for first order systems, we had the exact same result. In fact, I think what we said is for the first order system, although it was different, was that the pole was on the real axis. But we see in all these cases, if it's a first order a second order system, it really doesn't matter. The thing that matters, right, it's the real component of the pole, which is what we've seen all along, right? It's the real part of the eigenvalue or the pole, or however you want to think about it, of this system that matters, and that's what governs things like stability and doubling time and all these other performance metrics, right? And this is exactly how we can see this laid bare with actual equations, okay? Okay, so the last thing I want to do then is let's jump over to the computer, and I want to show you that I wasn't pulling your leg with all those hand-wavy calculations, and let's actually go do this in Mathematica, generate some of these plots, and just do a little bit of a sanity check. All right, so here we are in Mathematica, and again, I just wanted to prove to you that the solution that we cooked up on the board actually does satisfy this differential equation. Again, I'm going to scroll past a lot of these calculations. Feel free to download the notes and check these out if you want. It's several pages of just, boring algebra effectively, but like we said, at the end of the day, what we're really gunning for is all the way down here. Whoops, sorry, I think I passed it. Yeah, right here, right? This is what we had circled up on the board. We said that the solution to that original differential equation, it's just this single sine wave where the amplitude is this, funny constant, which is then time varying, and it's nothing more than a sine wave at a constant angular frequency of omega d with some phase shift, right? So here it is, we all wrote it down, and the claim is that this thing, right, by the time you make all these substitutions, yeah, sure, it looks ugly, but it's just a sine wave that has a time varying amplitude. That's all this thing is. And the claim was that this satisfies the original differential equation. So let's go ahead and check that, right? So I want to take its derivative twice, add it to 2 times zeta times omega n times its derivative once, times omega n squared times itself. That better equal 0 at the end of the day. And I got to make sure we satisfy the initial condition. So the function at time 0, that better equal x0. And the derivative of the function at time equals 0 better equal x dot 0. And you can see when you run this, it actually is true. So lo and behold, this is the correct function that satisfies it. Now, the other thing that maybe we'll do while we're sitting over here in Mathematica, let me just show you a couple of these plots. So all I'm doing here is I'm plotting that function. In fact, this is the exact picture we drew up on the board, including the function h of t and negative h of t, which was the envelope. But what we can do here is we can start messing with all these parameters. You can just see that as you change parameters of our function, it just changes the sine wave and it changes the envelope. So for example, if I change the initial condition from -2 to like -3, right, all that does is it just changes the initial position. You can also change the initial slope to be something. Whoops, I didn't want to hit play. I just wanted to keep this at some number. And more importantly, if you change things like the damping ratio, right, we saw that that changes the number of oscillations and it changes the envelope. Right, and you can see the envelope adapts appropriately, right? So I think all these calculations seem reasonable. It all is working. Everything seems to check out. And basically, at the end of the day, let's just scroll down here. I just wanted to summarize. Maybe what I did claim on the board that we would show is the actual plot of how the real part of the pole influences the time to double. So you can see, yeah, if you are close to the imaginary axis, mainly that the real part is small, the time to double is quite large. But as you start moving that pole into the right half plane just a little bit, this time to double starts going down drastically until you kind of hit this sort of asymptote, right? So that's kind of fascinating. And again, let's just put the summary. And in fact, I think after all this discussion, we can fit this entire lecture onto one page if that's what we wanted to. We said for a first order unstable system that looked like this, the time to double was just this, natural log of 2 over 2 over negative p, right, when p is negative. And then for our second order system, our standard second order system, in the case where we have an undamped and unstable situation, right, the time to double is, you know, it looks very, very darn similar. It's basically natural log of 2 over the real part of the pole, right? That's what happens in both these cases, in both equation 4 and equation 11. That's all it is. The time to double, it's just natural log of 2 all over the positive real part of the pole. So there you have it. That's it. And I think with that being said, this is probably a great spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. If you do subscribe, it really helps us continue to making these videos, and the new videos come out every Monday, so I hope we'll be able to catch you at a future discussion and we can all learn something new together. So until then, I think I'll sign off. Talk to you later. Bye.